So we now need to look at the dimension of the null space of a matrix and the column space of a matrix. So the dimension of the null space of a matrix is simply the number of free variables in the homogeneous equation matrix A times vector x equals the 0 vector. So we'll make a love note here to ourselves that the dimension of the null space of said matrix A is equal to the number of free variables. And looking at the dimension of the column space, we see that the dimension of your column space of matrix A is simply the number of pivot columns in A. So the dimension of the column space of a matrix is equal to the number of pivot columns. So keeping these two definitions in mind, let's take a peek at this example. So we're asked here to find the dimension of the null space of A and find the dimension of the column space of matrix A. Now looking at this matrix here, we see, hey, this is already in echelon form. So actually we're given an augmented matrix here, but we can still see the pivot columns. We can see we've got a pivot position in row 1 and row 2. So we can say that therefore matrix A has n equals 2 pivot columns. So therefore by definition this lets us know that the dimension of the column space of matrix A is 2. And that is our beautiful final answer for the column space. And so we can again make a little love note here to ourselves. Because we have 2 pivot columns, this means our matrix has 2 basic variables. But notice that each row here, right, we have 1, 2, 3, 4 entries in each row. So we have 2 basic variables and 2 free variables. So therefore, matrix A, without having to do any further solving, we can see has 2 free variables and so the dimension of the null space of matrix A is 2. And we know this is true because we think the basis of the null space will have those 2 vectors based on the column vectors associated with our free variables.